Okay, welcome everyone. It's a pleasure today to have Andy Kent from the Center for Quantum Phenomena from New York, who's going to tell us about a new spin of magnetism with applications in information processing. Andy, please.
Okay, well, thank you very much. Thank you for this opportunity to speak with you. I hope you can hear me clearly. I thank you, Hisham, for this invitation. I appreciate the chance. Also, I'm hoping that in this seminar, we can find some connections. I know that I've looked back at your previous seminars and I can see they're both mathematical and theoretical. I'm an experimental condensed matter physicist, even though I'm director of a group that has theory in it. So I'm going to tell you about some experiments with some topology in them at the end. So I'm going to tell you a story about magnetism and how spin is playing now a very critical role in magnetism research and in some of the applications of magnetism. And you'll see the work I'm doing is part of a large group. And I'll mention the people along the way and also thank them at the end. You'll see their names on many of the papers that I show. So I'm going to tell you a story about spintronics. This is a type of electronics which uses the spin of electrons, and then spin transfer torques, which are ways of exchanging angular momentum between itinerant electrons and magnetization. I'll talk to you about some of the basic phenomena that occur in a very simple structure called a magnetic tunnel junction. And then I'll talk a little bit about magnetic skyrmions, which are an exciting new area in this field where people can create these topological structures and then manipulate them with electrical currents. And I hope I have time to tell you a little bit also about the center at the end, what our center is and what our plans are for the near future. Okay, so first spintronics and spin transfer torques. I think this, since this is a colloquium, I'll start broadly and say that Einstein was one of the first people to realize the very deep connection between a magnetic moment, magnetization, and angular momentum. So what his concern is that it was in the early 20th century, was that there seemed to be two ways to create magnetic fields. One is by an electric current, a la Oersted, that is, you pass a current, you can see a compass needle deflect, and the other was with a permanent magnet. So it seemed like there were two separate ways, and so he postulated that in the materials themselves, there were currents that were generating the magnetic moments. And if there were currents, that means orbits of electrons around atoms, that means there was angular momentum important. And if there was angular momentum, it means that if you took a magnetic material and you changed its direction of magnetic moment, you'd be changing its angular momentum. And in such a way, you would expect then by conservation of angular momentum, the object would rotate. And this was an experiment he did with de Haas, and it's called the Einstein-de Haas effect. The idea is you take an iron bar, you magnetize it with a small field, you reverse the field, and the bar is hanging on a thread, and the thread rotate, and the bar rotates. And what he was trying to deduce was the relationship between magnetization and angular momentum. In fact, Einstein thought all of the angular momentum was due to orbits, which would have made this gyromagnetic ratio proportional with a G = 1. We now know G = 2 because the main component of angular momentum in a magnet is associated with the electron spin and has a G = 2. But the main point is he saw this connection, and in fact, he considered the iron to be molecules instead of a metal. So he was thinking of basically an insulator where each of the iron atoms was disconnected. And we now know that the electrons in iron are mobile. So there were many ways that angular momentum could be conserved. In fact, angular momentum could have flown out through if this was an electrical circuit, it could have flown through the circuit to conserve angular momentum. And this is actually an experiment you can do in an undergraduate lab. You take a small piece of iron and you alternate the field, and you can see that the bar rotates. So there's indeed an easy experiment you can do to show that there's angular momentum associated with magnetization. So I'm going to fast forward then to another important discovery. This was the discovery that if you have a set of layers, a multi-layer with iron and chrome, where chrome is essentially non-magnetic, and they're formed in layers where you have, say, about 20 atoms of iron and then 9 atoms of chrome, repeated. If you magnetize that layer, so you start in a situation where the irons are oriented anti-parallel, so their magnetizations are anti-parallel, and you magnetize it, you can see a huge change in resistance. This is called giant magnetoresistance. It's a factor of 2 change in resistance at low temperature, and can be almost that big at room temperature as well. So the same experiment was done by Grunberg. This was by Ferdinand, this is by Grunberg. He showed that if you take just a 3-layer system with iron, chrome, iron, starting in an anti-parallel state, you have a high resistance. And then if you magnetize it, the resistance drops by several percent sharply. And this was the first realization that spin can play an important role in electronics. I'll tell you about this, because it's actually the fact that the electrons are polarized in the magnetic material, and they can transport their polarization when a current flows that gives these magnetoresistance effects. And this was discovered in 1988 and awarded the Nobel Prize in 2007. It's much easier to understand this actually from a point of view of electron tunneling. The so-called magnetic tunnel junction, where you have 2 metallic electrodes separated by an insulating layer. So imagine this is again iron, and this is iron. Because the electrons in iron have a net magnetic moment, that is to say, there are more electrons with their angular momentum aligned with the net angular momentum of the material than anti-aligned. When the layers are oriented parallel, you have more electrons of one type transported across the barrier than the other type, assuming that the spin is conserved in this process. If you have now an anti-parallel arrangement, you have a situation where, in fact, there are less available states for electrons with one spin to tunnel into in the opposite side. So a so-called Stoner model of an anti-ferromagnet would be there's a greater proportion of a majority electrons with their magnetic moment, say, up than minority. And in a tunneling process where electron spin is conserved, you'll have different tunneling conductances depending on the magnetic states of the electrodes. So say high density of states going into low density of states and vice versa. And you can show in a very simple model that the change in resistance when you go from parallel to anti-parallel is related to the spin polarization of electrons at the Fermi level. So at this level here. And so you can decide a polarization factor for the materials, and you can show that the change in resistance, the anti-parallel resistance minus the parallel divided by the parallel, is related to this polarization. Now, for ferromagnetic metals, the polarization is about 40%, 0.4. So this factor can be about 40%. In fact, what you find when you make a structure, and this is something here that's done this is an experiment done in my lab. You have a thin MgO layer separating now an alloy, cobalt iron boron and cobalt iron boron. You can find factors of 3 change in resistance when you magnetize the layers, when you go from anti-parallel arrangement to a parallel arrangement. So this can be a significant effect. And this is actually an effect because not only do you have the tunneling spin polarization to consider, but if you have a crystalline structure, you have certain selection rules in the tunneling, namely momentum transverse to the barrier is conserved, and that can give you a very, very large magnetoresistance. In other words, you don't sample uniformly the Fermi surface of the materials. And this was proposed theoretically in a paper which looked at the electronic structure of iron, MgO iron, and then seen experimentally a few years later. So this is a case where really theory-led experiment where electronic structure showed you could have really large effects due to the electronic states of particular materials and selection rules in tunneling. So that's the situation maybe in 2000 or around that time. And then there was this amazing idea, basically around that time, 1989 to 1996, that if you have flow of angular momentum, when you put a voltage on, you will also exert torques on the magnetic moments. In other words, you will exert forces on the magnetization that can realign it. So the thinking again, if you think back to Einstein again, you can not only not only can you flow angular momentum by remagnetizing something, but you can flow angular momentum by having itinerant electrons flow that transport angular momentum. And John Slonczewski and Luc Bourget were awarded the 2013 Oliver Buckley Prize. That's the highest prize in condensed matter physics that the American Physical Society gives for predicting these spin transfer torques and opening the field of current-induced control over magnetic nanostructures. What was exciting about this was a new way to magnetize materials. And previously, the only way to magnetize materials was to apply magnetic fields. And this is saying you can actually magnetize materials by flowing angular momentum by currents that you create by polarizing electrons. I think the most interesting paper is this one, 1989, because it's a very fundamental paper. It's a paper people taking basically graduate level quantum mechanics, maybe even undergraduate level quantum mechanics can follow. It considers electron tunneling through a vacuum barrier, where the electrodes are materials, electron gases, where there's a large magnetic field applied. The large magnetic field is taking into account the exchange field. In other words, it's an internal field that creates the magnetic moment itself. This is a Stoner model of a ferromagnet, and the theory now allows that the two magnetic fields can be at an arbitrary angle to one another, and so now you have tunneling, and you consider the flow of electrons as you vary this angle. And what he found is this Julier magnetic valve effect. That is the tunneling formula I showed you earlier, where the tunneling magnetoresistance is related to the polarization of electrons at the Fermi level. And then he also found that the two magnetic moments are exchange coupled. So in other words, they're not independent layers. They actually feel an exchange interaction that tends to align them relative to one another. And that's essentially because there's wave function overlap between the two electrodes. And the third effect is this new effect. It's an effect, he called it an irreversible exchange term in the coupled dynamics of the ferromagnet. And he said for one sign of the external voltage, this describes relaxation of the Landau-Lifshitz type. And for the opposite sign, it describes a pumping action, which causes spontaneous growth of magnetic oscillations. So he's saying that for one voltage, you will start to inject essentially spin and cause the spins to precess. So he has a picture like this. These are the two magnetic moments of the layers, A and B. There's a spin current. If the two layers are the same, the spin current is the average or of the angular momentum of the two. And then if you pass a current, you get this windmill effect where the layers start to rotate. In fact, in practice, what we do is we fix one layer, so only one layer can rotate. And what's exciting is this provides not only some interesting physics, but it also has applications which now are being developed worldwide, because you can go in and pass a current and switch the direction of the magnetic moments. So write information, and you can go back and read that information by working at low bias, a low bias voltage, not enough volt just to measure the resistance. You can determine whether the state is P or AP, parallel or anti-parallel, by whether it's a high or low resistance state. So this is exciting. The basic idea, again, is conservation of angular momentum. You get a flow. If you have a flow of electrons and they encounter a ferromagnet, the ferromagnet tends to filter the electrons, so they come out polarized in the direction of the ferromagnetic magnetization or angular momentum. If there's a change in angular momentum of the electrons, there can be a back reaction on the magnetization to conserve angular momentum. And you can show that that back reaction corresponds to a torque that's related to the amount of angular momentum each electron can deposit, which is h bar over 2. times the number of times the polarization of electrons times the angle through which they are rotated when they go through the layers. So this would be the best case scenario where all of the angular momentum goes into the magnetization of the material. And of course, there are other source ways that the material can lose angular momentum through phonons and other processes. So this is really the best case. You create the polarization usually with a second ferromagnetic layer, and that sets a polarization. And that also now allows you now to determine what happens, because if the relative orientation of these two layers changes, there's a change in resistance through this tunnel magnetoresistance effect or giant magnetoresistance or other effects. So you can both detect and create this this dynamics of the magnetization with currents in a structure like this. The structures generally have to be small because you need really relatively high current densities, and you want the spin polarization to be the dominant effect, not fields generated by the currents. Okay, so this shows a small animation one of my colleagues made. The electrons go through, they polarize, and that leads to angular momentum or torques that change the magnetic moment. If you want a little more sophisticated picture, you can think about the magnetic moment on a block sphere, and relaxation of the Landau-Lifshitz type corresponds to this black arrow, where it's a uniaxial magnet, where the easy axis, say, is north-south here. If I let it go, it will spiral and eventually align. If it was a quantum spin, it will just keep rotating forever if it doesn't interact with anything. But in a real material, there's dissipation. There's always dissipation in something, so the magnetization relaxes. If the current exceeds the threshold, you compensate this damping, and then the precession angle grows, and eventually you reverse the direction of the magnetic moment. And if you have a very large current, then this precessional reversal happens in fewer cycles. And you can work out, based on a theory that Slonczewski put forward, what the threshold current is for that switching. It's related to magnetic material parameters like the anisotropy. It's related to fundamental constants. It's related to dissipation, this damping parameter that I mentioned. And you can show that if you have a uniaxial magnet, a magnet with two states up and down, separated by a barrier, the threshold current is directly related to that barrier. So if you take a barrier that's 60 times K times T, which T is room temperature, you get a threshold current of 15 microamps, which is relatively small, so that's one of the exciting things also, that it can be created with a relatively small current, so you can make it miniature in size and operate and deliver this current with a small transistor. There are other things that can happen that are interesting. You can create spin wave excitations. So if you don't pattern one of the layers and you make what's called a nanoconstriction or a nano contact, you can excite spin waves, and those spin waves can radiate away. So you also have a way of transmitting information or creating excitations in the magnetic material using these kind of effects. So let's go back to the full screen. So this is the picture. Then you pass a current through a nanopillar, you can get it to switch. The spin current polarization is related to the polarization of one of the layers of the magnetization. Now it turns out you can also generate these spin polarizations using what are called spin orbit torques, or using what's been called the spin Hall effect. That is, if you pass a charge current through a metal with strong or other materials with strong spin orbit coupling, you get a transverse flow of spin. So just like in the Hall effect, a charge current leads to a voltage accumulation. Here, a charge current leads to a spin accumulation. And so you can have these torques where the current doesn't have to pass through the magnetic layers themselves. It can pass adjacent, and you can create these accumulations and these torques. So a little bit of the math. Here you have a current density, a spin current density that's related to the polarization of the materials. Here you have a spin current density that's related to an angle, the so-called spin Hall angle. And you can show actually that the spin current here, which is now the current density times the area, is also related to the polarization. And here you get a geometrical factor where the actual current, because the currents flow in different geometries, different cross sections, you can get an amplification of the actual spin current by the dimensions you're injecting into divided by the thicknesses of the layers. And spin current is a tensor, so it has a flow direction and a polarization. It's the outer product of those, and here the polarization is set by some layer. In this case, I'm calling it the reference layer. It's a thick layer that doesn't respond to the torques. And here the spin polarization is set by geometry. In the case of the spin Hall effect, it's set by the direction you apply the electric field to generate the charge current, and Z, and that's the polarization, and the flow direction is in Z. So here you're geometrically constrained, and here you set the polarization with the ferromagnet. So the equations of motion are like those of a spin, a quantum spin. You have this is the most basic you can imagine. It's called a macrospin model, where you neglect spatial variations in the magnetization. You have precession of the magnetization around some effective field, which is due to anisotropies or applied fields and other terms. There's damping term, which is just friction. It's phenomenological. We have some understanding of where it comes from, but it can depend on many factors of the material. And we have this new term. This is the so-called Sonsuski term, this term that injects energy into the magnetic system, and it corresponds to the absorption of angular momentum that's transverse to the magnetic moment of the material. And so you get interesting nonlinear dynamics. You get there's a threshold current when this term exceeds this term, and that you can. And there's also the possibility of having so-called non-adiabatic torques that are basically field-like torques, or torques where these factors are both proportional to the current, where the magnetic moment precesses about the polarization. So you get this fast motion, which is the usual gyroscopic motion. You have damping, and if these two are collinear, if the effective field and the polarization are in the same direction, then they just oppose each other, and you get this picture where the damping and spin torque can either oppose or enhance each other depending on the sign of the current. Again, for one sign, you would just enhance the damping, you damp more quickly to the effective field direction, and for the other sign, you create these excitations. Okay, so there's a whole zoo of things you can do here and look at. You can create these spin waves. The main thing is you need small dimensions, you need large current densities, and you want small currents, so that means small dimensions, typically tens to hundreds of nanometers. You can excite spin waves. You can make these nanopillars. You can even do this kind of effects are not necessarily, you don't need two layers. You can actually see these in one layer. And by the spin Hall effect, you can create these excitations, and you can make oscillators where you confine the material in some way, and you can cause the spins to oscillate in a region and generate spin waves. So there's lots and lots of physics and interesting applications of these kinds of effects. So maybe I'll spend now a few moments. I know that I don't know if this is a good point for questions. I'm not sure if you want to ask questions at this point or wait till the end. I'm happy to take questions during the talk, or you can put them in the chat.
Do you need to ask questions? Or should we wait till the end?
Andy, I think we should wait until you're finished, until the end.
Okay, sure. Okay. I hope the pace is okay. It's all good. Okay. All right. So let me talk about magnetic tunnel junctions. And I know that I am talking to a broad group, so I hope this is understandable. And so I'd say one of the big advances now was really the ability to make these kind of materials. I think if you told someone, 20 years ago that you were going to make a crystalline barrier that was 3 atoms thick and didn't have any pinholes in it, they would say you were crazy. This will never happen. People have been working with what are called aluminum oxide barriers. They're amorphous barriers. You just oxidize aluminum, but they oxidize naturally, so you don't get pinholes. So here, but it's doable, and people have succeeded now in making these layers have to be extremely smooth, nearly atomically smooth. So this is cobalt iron boron, MgO cobalt iron boron, like the structure I told you, and then it's patterned so that you make this into a pillar. So it's 40 nanometers wide and maybe 5 or 10 angstroms, 5 or 10 nanometers tall. And the main layers are just several nanometers. And as I showed you, you can, by applying magnetic, you can make one layer very hard magnetically, so it stays fixed, and the other layer then can be switched with a relatively modest field here, not so modest, actually 0.4 Tesla, and switch back. There you can see there's a small offset. That's because one layer exerts also an exchange or a dipolar field on the second layer. And then you can take this and also switch it with current or apply a bias voltage and see that you go from a high resistance to a low resistance state here at 400 millivolts, and back at about 180 millivolts minus, you go back to the original AP state. So you can go between the same two states with magnetic fields. You don't need magnetic fields anymore to change the state. And again, the application is MRAM. You would create a junction and access it with a transistor. So you would select the device you want to do with one transistor, and all the materials here are actually compatible with semiconductor what's called back end of the line technology, which means it's after all the semiconductor is done, you add the metals, and the tunnel junction can be part of that. So this enables integrating memory and logic in a new way. Okay, so how does it work in experiment? What you can show is that that if you look at the current required to switch divided by the threshold times the pulse time. So this is now what you imagine here, what you do in experiment is you apply an electrical pulse anywhere from 100 picoseconds up to milliseconds, and you ask how long does it take? What is the threshold for switching? So as you go to shorter times, shorter pulses, nanoseconds, the current or the voltage required to switch goes up. So the faster you go, the more voltage you have to put. And if you plot the voltage you have to put, the overdrive, I over IC or V over VC, you find that 1 over T, 1 over the pulse time, is proportional to the pulse amplitude. And this is actually just the statement of conservation of angular momentum. You have to, at short times, you have to put a certain number of charges through, where the number of charges is roughly equal to the number of magnetic moments that you have to switch. It's the number of charges, which is I times T, that it's a fixed roughly a fixed quantity. If you go into detail, you find that actually there's really interesting dynamics of the junctions. They don't switch uniformly. They form little droplets. This is a simulation that we've done and modeling we've done. They form droplets. You can form domain walls, and you get all kinds of interesting dynamics of the domains during the switching. But the conservation of angular momentum is more or less followed even when you have this complex dynamics during the switching. So this shows an example then of a structure. These are the junctions. This is the top electrode. This is the bottom electrode. That little white area, that's the MGO, and this is 60 nanometers, 49. This is dielectric, so the current is flowing perpendicular to the layers. And here's there's a 22 nanometer structure where the top is not it's still buried in dielectric. What you have to do is sand it very carefully with a chemical mechanical polish, and then make a top contact. And you can find that the resistance goes up. That's because the area is going down. But the resistance area product is fixed. It's set by the junction properties. So you can study this, and you find indeed this is now experiments we do in my lab. You look at what is the pulse amplitude required to switch. The color here is the switching probability at room temperature here, and red means it didn't switch, black means it switched, white means it's at the borderline. This border now is indicated by the blue points. We actually use a kind of smart algorithm to find this 50% switching boundary and to take a high density of points. And you get this 1 over T, 1 over pulse duration behavior when you look at the dynamics of the switching. And you can show basically that the 1 over the pulse time is related to the overdrive, Y minus IC divided by IC. And there's a critical number of charges you have to put in. You put n charges in, and part of that angular momentum goes into dissipation. This IC is related to the damping. So this is the conservation of angular momentum for this particular system. In fact, the switching is also stochastic. So it's because fluctuations of the magnetic moment play an important role. These are very small magnetic elements that fluctuate thermally. In fact, you even need fluctuations to initiate this switching. So you find even if it switches, at some amplitude, there's always a probability that it didn't switch. And this is again an interesting statistical physics problem actually to understand how the error rate depends on the conditions of the sample. And this is one I worked on with my colleague Dan Stein at NYU, who's a statistical physics and studies rare events and the statistics of rare events. You can reduce the amount of energy required if you reduce the angular momentum. So if you take a magnetic material like permalloy, that's nickel iron, and you dilute it with copper, you reduce the angular momentum of the layer, you make it less magnetic, and you then reduce the amount of current you need to switch. And this is in fact what you find, that you can reduce the threshold by reducing the angular momentum in the layer. You can also switch. You can also do what's called precessional switching. This has been an idea that I proposed in 2004 that took many years to realize. It's like many of my ideas that they sound good on paper, but they're actually much harder to realize than they seem at first. The idea was, when you want to change the direction of a spin, you don't apply a magnetic field along the axis of the spin. You apply the magnetic field perpendicular to the spin. Like if you're doing NMR, you want to flip a spin, you apply the field transverse, and then the spin will start to precess. So the idea here was to inject spins that are perpendicular to the free layer to cause the spin in the free layer to precess. And then you could imagine much faster switching. In fact, switching on the time scales of just 50 picoseconds set by precession times. And in fact, that does happen. And this is an example then of an experiment we did where we built this kind of structure. And we did the same experiment I showed you earlier. We look at the switching probability as a function of pulse duration. Now this is at low temperature, 4 Kelvin. And you can see doesn't switch, switches, doesn't switch. So you see bands of switching and not switching, which are consistent with precession of the magnetization. This shows the experiment, the oscillations in the switching probability. And then to model this, we actually had to assume there was far more thermal fluctuations than just temperature. So our temperature of the experiment was 4 Kelvin. We needed to include a lot more noise in order to get the oscillations to wash out as they do in the experiment, which is after just about 5 or 10 cycles. But the basic concept works. It requires more current, but you can get this kind of precessional dynamics with these spin transfer torques. So I know this, so that's just kind of maybe hitting the highlights of spin torques. You can see you can manipulate spins. They're macro spins. They're 10 to the 5th or 10 to the 6th magnetic moments. They're not individual magnetic moments, but you're manipulating them with electron spins. And maybe on the last part, I'll talk about something topological, since I know that's your title, and I'll show you something that what we done recently with what are called magnetic skyrmions. So magnetic skyrmions are a topological structure in magnetic materials, which form this kind of whirling structure. You can think of them as kind of the regions, say, where the magnetization down and rotates up in such a way that this has a well-defined topological index, a quantity, a topologic index of 1 or -1. And so these are protected in some way. In order to erase them, you'd have to break some exchange interactions. And in a continuum model, they would be fully protected by their topology. They happen in materials with lack inversion symmetry, which have what are called Dalachinsky-Marina interactions that these are exchange interactions that are not isotropic, that have a form SI.Sj, where Si and Sj are neighbors. So Si cross Sj, where I and J are neighbors. And so this tends to favor spins which rotate in one sense or another, depending on the sign of D. You have the usual Heisenberg exchange, the Deleschinski-Marina interaction, and then you have anisotropy, which leads to this preferred direction of the spins along some axis. And if you work out now what are the ground states in a model like this, or what are the possible metastable states, you find actually, even with this really relatively simple Hamiltonian, a large number of possibilities. You can have materials where you have, which are no skyrmions, there's just uniform magnetization. You can have so-called bubble skyrmions. These are, stripe phases. These are phases where the magnetic dipole interactions play an important role. They're not even included in this Hamiltonian that I wrote down. They're straight, and then stray field skyrmions. These are where dipole interactions lead to the formation of skyrmions. And then you have skyrmions which are favored by this Deleschinski-Marina interaction, these DMI skyrmions. And for some of the interest has been in trying to make isolated skyrmions where you can either have a skyrmion or not have a skyrmion in an otherwise uniformly magnetized material. And the idea would be you could move the skyrmions around and they could be an information carrier. So you would have a track where you could put skyrmions, displace them, and then read them. You might read them with a magnetic tunnel junction. And that could be a form of memory for those like me who grew up with cassette tapes. This would correspond to, instead of moving the magnetic material, you would just move the information of the magnetic material. So you would use current to displace it. There would be no mechanical motion, but you could displace the magnetic material. So it turns out spin currents are a very effective way of moving a magnetic skyrmion. So this is because of the form of the interactions of spin currents. And so what we've done here is actually we built samples where it's the degree of inversion symmetry breaking that determines whether you have this DMI. And so what we did is we built samples where we could control the degree of symmetry breaking. Cobalt gadolinium is a ferrimagnetic material, and by deciding what to put on top, we could make either materials with no small DMI or large DMI, or actually control the DMI in the experiment. So we create these structures, and then we pass currents. We're using ferrimagnets also, so because we can, the ferrimagnet in some ways is like an antiferromagnet at a particular composition or temperature. For a fixed composition, the magnetic moment vanishes. So you have no stray fields. So your main interaction would be DMI interaction, this anisotropic exchange interaction. And also when the angular, and there's also a specific temperature where there's angular momentum compensation. So then you expect that very small currents would be able to move magnetic structures because not much angular momentum is needed. So this shows an example that of magnetic measurements of some of our samples. You can see the minimum in the magnetization corresponds to the magnetic compensation, and then there's an angular momentum compensation that's nearby, associated with the different G factors of the cobalt and gadolinium in this amorphous alloy. We did a lot of experiments. I won't bother you with this, but one of the key things we found is we could control DMI, and with the control of DMI allowed us to control the skyrmions. So we built a little microscope that allows us actually to see what's going on in these samples. So this is the microscope. There's a wire down here which brings the currents we want to apply. This is a ground signal ground. So we apply currents from the signal line. They come around here. So this is where we're applying currents. And then we look at the sample with this microscope. So this is one of our gadolinium structures. It's about 5 microns wide. We're passing, and these are gold contacts, and we pass current, and we can actually look and see what happens when we do that. So this is an example of a domain wall. We can nucleate a domain wall and then move it around. We can move the domain wall up or down depending on the polarity of the current. And again, you could show actually these spin currents can be very effective at moving the L-type walls. So you can show that by changing the L-type wall into a block wall and seeing that it moves very ineffectively. And you can move these domain walls relatively quickly, up to 400 meters per second. And we can understand aspects of this curve. We can change the materials. This, in this case, the spin currents are injected by the spin Hall effect. And the materials here are determining that both the spin Hall effect of works and the DMI that's setting the type of wall. So basically the current, the wall velocity depends on the current, and at some point it slows down as we heat the sample up, and this magnetic moment and angular momentum again increase. So we have all these different regimes we can understand and try to understand. And we've been able to show that we have relatively, and this is one exciting thing, is we could actually create skyrmions. This is a work done by a postdoc in my group, Yassin Kassab. He showed that he can nucleate skyrmions. In this case, the skyrmions are nucleated thermally. We believe we're just heating the sample up and then almost close to its ordering temperature. And then as it cools down, we sometimes form skyrmions. We can show their skyrmions by the way they move. Actually, they move in response to currents, just like the domain walls. You can look at their profile, and they also have. You can also. This is with our. I guess this is with our. Let's see. This is the dimension here. This is with our microscope, and we've been able to also image them with X-ray imaging, where we can see extremely small skyrmions. Smaller than the optical size of our basically 250, 200 nanometers wide. So these move, they move also, they move both up and down, and we can get two of them, sometimes one of them. They exhibit what's called the Skyrmion Hall effect. That is, when we pass a current, they tend to displace left or right. And this is also a sign of their topology, the fact that they actually are moving left or right. And these skyrmions actually can be displaced almost as fast as domain walls in these wires. So we reported the highest skyrmion velocity, about 600 meters per second in these samples. Okay, maybe I'll say something. I mean, we did quite a bit of analysis. I won't tell you about it too much here. But I think one of the exciting things is we can now control these topological objects in magnetic materials, and that can potentially be useful for a whole host of things. It can be used as a way. We've thought about how we can use these skyrmions now to implement some kind of quantum operations, such as braiding. So an idea would be to put these magnets with skyrmions in proximity to a superconductor. That induces an exchange interaction on the superconducting state, and there are predictions that there should be a Majorana modes that form at the boundary of those when you have that kind of exchange interaction on the superconductor. So you could imagine that each of those skyrmions has a Majorana mode. And then if you can manipulate the skyrmions with current, you can also do operations, quantum operations with the Majorana modes. This is, I think, far out, but not out of the question. In fact, we've been working with my colleague Javad Shabani to implement this. He has indium arsenide, aluminum arsenide heterostructures where he has evidence for these Majorana modes. And we've been trying to put skyrmions in proximity to that indium arsenide superconductor. And here's the magnetic force image that shows kind of a disordered lattice of domains and skyrmions that are on a superconducting layer. So we think there's potential for these skyrmions to be used as objects for quantum operations. I work with a lot of people. I mean, one thing we've done is we've created an international laboratory which is focused on nanoelectronics and low power electronics, using spin torques, using strain, moving domain walls, using light to manipulate ultra-fast optical pulses to manipulate magnetization. This consists of people at UCSD, Eric Fullerton, University of Lorraine, Stéphane Mangin, University of Paris-Saclay, Daphne Sonia, and we exchange students. We also go between our institutes when we can to do this. Let me talk in the last few minutes. Let me say a few words about the Center for Quantum Phenomena at NYU. So this center now consists of 7 faculty. They're listed here, and our pictures are here. We do experiment in theory. We have really outstanding theorists. Aditi Mitra Drisel is a recent hire who's joined with the Center for Computational Quantum. That's a center at the Flatiron Institute next to NYU, and he does quantum information theory. Aditi Mitra does non-equilibrium quantum physics related to basically how you understand systems driven far from equilibrium. Andrew Ray does spectroscopy, and Dan Stein, as I mentioned earlier, is a statistical physicist doing physics of rare events. So our center started in June 2017. We officially opened our center in September 2017, and we were able to have the center because the physics department moved to a new building. Maybe some of you have been here. It's the top 3 floors of 726 Broadway, which has expanded the space available to physics by about 30% and given us really a beautiful laboratory space here. And this year, we are searching for 2 experimentalists in quantum condensed matter and ANO, and we have faculty. We have ties to faculty at NYU Shanghai. We'd love to have more ties to NYU Abu Dhabi. And we have affiliated faculty at the NYU Tandon School of Engineering. So we're excited that we're able to expand. We have beautiful lab space, and we're hoping to have a successful recruiting season this year. Okay, so to summarize, I've given you, I think, a whirlwind tour of some of the things that interest me in spintronics and magnetic tunnel junctions and magnetic skyrmions, and also told you a little bit about the Center for Quantum Phenomena at NYU. There are many people I've worked with and have contributed to the work, this is a growing list of people who we've worked on many projects together. So I won't name them, but you'll see them when you look up the papers that are associated with this talk. And I'll stop there. Let's see, do I have any pictures? No pictures. I'll just stop there.
Thank you, Andy.
So Andy, can you hear me?
Yes, very well. I can hear you really well.
Oh, great. So yeah, they fixed the microphone in the room. Yeah, thanks for your patience. Yeah, thank you so much for this talk. It's very interesting to hear these experimental and technological perspectives. And of course, we're happy to hear about the center, of course, in New York, and we're very interested in having further interaction and collaboration between the 2 centers. It would be delightful. So let's open it up for any questions from the audience. Of course.
If I speak, do you hear me? Hello?
Yes, I can hear you.
You hear? Great, excellent. I have one question about the creation of the Skyrmions. On one of the first slides where you introduced them, you had this cartoon picture of a Skyrmion writer that wrote them on a kind of tape, which gave the impression that there's of a very controlled way of creating them. But then later you mentioned that essentially, if I understood you well, you somehow heat up the material as it cools down. Some Skyrmions just form by chance, if I understood you well. Could you maybe clarify that? Or?
Yeah, that's a great question. I mean, indeed, we had hopes that we would be able to actually deterministically write these skyrmions. We have actually, so there are groups that have demonstrated a kind of a deterministic write, or with different ways. Spin injection should be a way to write that. We weren't able to do that experimentally, but other groups have. And people also use laser pulses and other techniques to write, essentially, by just transferring angular momentum or even heating locally. So it is possible to do this, but no one has made this full structure. No one has actually demonstrated a fully operational write, displacement, read. each individual component maybe has been demonstrated, but not in one unit. I would say that's the status. We did some modeling work that showed by creating a nanopillar and injecting spin, you should be able to create this topology. That is, you need something. You need to you need to go from zero topology to some topology. So there are ways, you need something special and somehow to create this. I mean, one way, of course, is as I mentioned, just making it disordered and heating up. You can create this, but indeed. So maybe I've answered your question. We didn't do it, but each of the individual components has been shown experimentally.
Can I maybe ask one follow-up? You also mentioned, I was wondering about this while you were speaking, and then you briefly mentioned this idea of braiding the skyrmions around, of checking that in the lab. But is there a theoretical reason actually to expect that anything happens? Like from the theory side, would we not expect that braiding them around has no effect? I mean, no.
Yes. Yeah, maybe I didn't quite. Could you say that again? Would you expect from the theory side? What? Please repeat the question.
Is there any theory of skyrmions that would predict that braiding them around each other has any non-trivial effect?
Yes, theory predicts it. There's a prediction that moving these skyrmions around, if they have the appropriate, if indeed the skyrmion has associated with it, if the skyrmion exchange interactions can be imprinted on a superconductor, then you would have highly non-trivial effects. There's this communications physics paper that describes this braiding operation with skyrmions. So there is a prediction that would be highly non-trivial effects if you could move these skyrmions in a controlled way. There's the several steps. One is the idea. One is the demonstration that first of all you do get a non-trivial quantum state at the core of one of these skyrmions. And then the second aspect of the theory would be what happens then when you braid those objects.
I see. Thanks.
Any other questions?
And if you need further references, I can provide them. You just send me an email. There are several papers. There are not a lot of papers, but there are several papers that explore these ideas.
Great. Sounds good. No more questions? Okay, let's thank Andy again for the very nice talk.
So yeah, I guess